Okay, so the final segment of compounds and their bonds. So up to this point, we've talked about different types of bonds. We had ionic and covalent. We've talked about molecular structures and how to draw them. And the next thing we're going to look at is electronegativity. Now, electronegativity is the measure of how strongly the atoms attract electrons in a bond. So if we think about a covalent bond where we're sharing electrons, the idea here is that those electrons are not being shared equally. Some atoms, for instance, the more electronegative ones, the ones that are closer to the right-hand side, starting with fluorine, will attract the electrons much more strongly than other atoms. And so, of course, if fluorine then gets into a bond with another covalent bond or another non-metal, then the electrons will be more shifted towards the fluorine. Now, the bigger that difference is, then what happens is we generate what we call a polar bond. Okay, so we have a range. So we're going to do a quick math equation where the numbers have a fixed value. You don't need to memorize those values. I'll provide those values for you. But you'll subtract the two, and then it's going to fall into one of these three categories. So either that difference will be between 0 and 0.5. If so, we call that a covalent nonpolar bond. So there we're saying that the electrons are being shared pretty equally. The second range is 0.6 to 2.0. This is going to be our covalent polar bond. So now the electrons are being shared, they're just not being shared equally. They're spending more time with one atom than the other. Anything that's above 2.0 is automatically ionic. That means they're no longer being shared, they've now been transferred. Now, there should be a figure on page 135 that gives you the periodic table with all the electronegativities. It's also something you could Google real fast. If you type in electronegativity values on a periodic table and then look at images, typically you'll get several options you could use. Now, how do we show that a bond is polar? So I'm going to get this number, and then what does this number mean? Well, okay, it tells me it's a polar bond, but what does that really mean? Well, what it means is that we have a partial charge. So it's not actually ionic, but there is a partial charge, a partially positive or partially negative charge. So for instance, if I look up HCl, hydrogen is going to have a value, and I'll go ahead and look that up for electronegativities real quickly. So again, I can go to Google. And under Google, just type electronegativity. And right away it popped up with a chart. I can go look at the images, pull the chart up, and depending on what chart you get, you will get slightly different values because they're man-made values. They're based on fluorine being the most electronegative. But from the one I've pulled, hydrogen has a value of 2.1. Now there's no units here, it's just an electronegativity value, so we're not going to worry about the units. For chlorine, the same table says it's 3.0. So we have 2.1 and 3.0. So now what I want to do is just subtract those two. So I'm going to take 3.0, subtract 2.1, excuse me, and of course I get 0.9. Now that's my difference right there. The 0.9 is telling us that this is going to be a polar covalent bond, right? Because it's between 0.6 and 2.0. Now, how do we show that it's a polar bond? Well, first thing, again, we're going to use a partial positive. So we're using a little delta with a little plus sign after it. That tells us when it's partially positive. So at this point, which one's partially positive? Well, the hydrogen only has a value of 2.1, and the chlorine had a value of 3.0. So the higher that value, the more they want the electron, the more the electrons would be here. So if the electrons are here, then the partially positive should be the hydrogen. And now we'll also use a partial negative. So now we have a delta, again a little delta but with a negative sign, and that one's going to go on the chlorine. So this is one way to show a polar bond. There's another way, All right, we know that the chlorine is pulling harder on the electrons, and so what we'll do is we'll draw an arrow. I'm going to emphasize that arrow a little bit here. We'll have an arrow that points to the chlorine. And then we'll take a line and point it here. So it's the cathode pointing to the electrode. So it's showing us the charge. So my electrical engineers, you're very familiar with this type of terminology and signs. But there you are. We're showing that the electrons are flowing towards the chlorine. Okay, so the arrow is simply telling us that the electrons spend more time near the chlorine than the hydrogen. Okay, so that's electronegativity in a nutshell. So we can do that with any bond. Now we only assign electronegativities to bonds. So let's say I want to look at something like CO2, right? Now carbon, remember, had two oxygens connected. So that means we're going to have two arrows pulling in opposite directions towards those oxygens based on the values. So I'd have to look up the value for carbon, look up the value for oxygen, subtract the two, and see where that difference falls on that scale. Now, the next thing I want to look at is called VSEPR. Now, VSEPR is valence shell electron pair repulsion. And what this is going to do is predict the dimensional geometry of the molecule. Okay, the name is simply telling you the theory itself. We're basing it all on the valence shells, so we're really looking at the outside electrons. And then we're going to see how electron pairs repel one another. So remember, we talked about spin when we looked at electron configurations. They could spin left or they could spin right, which means two electrons can get fairly close to each other. But once I have a pair, nothing else can get near them because now both of those pairs have an angular momentum that says no to everything else. Okay? Now, from that repulsion, we can then calculate the angles of the bonds. Now, I'm not going to worry about the numbers, but you are going to have to worry about shapes because some shapes will actually cancel the effect of polarity. So based on the number of pairs around the valence electrons, both bonded and unbonded. Remember, an unbonded pair is called a lone pair. We're not new to that. And now I want to draw out a molecule. So the way we've done this so far, if I draw out CH4, I would go through the halves and the ones. I'd find out I have 4 bonds. And then when I draw it on a piece of paper, it would look like that. Now this is not really what it looks like, but this is how we draw it on a piece of paper. Right? We have single bonds all filling all the atoms. There are 4 pairs of electrons and they're all pushing away at each other. Right? They're trying to get away from each other and get as far away as they can. So is 90 degrees as far as they can get away from each other? Only if we were in a 2-dimensional world. But we're not in a 2-dimensional world, we're in a 3-dimensional world, which means the furthest they can get away from each other is actually 109.5 degrees. So rather than being 90 degrees, they can actually get an extra 20 degrees and get up to 109.5. Now again, I'm not worried about the actual angle. What I'm more concerned about is the shape, okay, and how to understand this stuff. So in order to pop that drawing out into 3 dimensions, there are some things we do to give it some structure. So here we have the carbon in the center. We see a regular line to that hydrogen. That regular line is telling me that the carbon and the hydrogen, they're in the same plane. Now, these other 3 hydrogens are not in that same plane with these 2. This one is called a wedge, and it's sticking away from us. Right? It's getting bigger as it comes out. That means it's coming, sorry, not sticking away, but sticking towards us. So this hydrogen's coming out of the board is what that drawing is telling us in that shadowing. This hydrogen, notice the wedge is coming up to the carbon. That means this hydrogen is actually back behind the board. Same with this one. So these 2 hydrogens are actually back. This hydrogen is coming forward, but this hydrogen is in the same plane, right? This is our basic shape. And our basic shape is called a tetrahedral. Now, when I say basic shape, it's because we are sticking with just the main group elements, the octet rule. So if I only have 8 electrons, that means I only have 4 pair. 4 pair then, that basic shape is going to be a tetrahedral. The tetrahedral is a pyramid with a triangular base. Okay, now this is going to be the same shape for everything that has 4 pairs. However, will I always have 4 things connected? And of course the answer is no. So the next example I give is ammonia, NH3. And notice now we have a lone pair. The lone pair is now in the plane with the nitrogen. And of course these things can rotate. So I don't have to keep this one in the plane. I could rotate this one here and rotate a hydrogen up there. That's fine. But the general idea is since we have a lone pair there, you still have the basic shape of the tetrahedral. but I can't see lone pairs. Lone pairs will actually spread out as well, pushing those other three hydrogens a little tighter. Again, I'm not worried about the numbers for the angles though. I am worried about shape names and understanding how this is going to affect electronegativity. Now, this shape is called trigonal pyramidal. So now we have 3 bonded and 1 lone pair, still 4 electron pairs, right? So if we have 4 electron pairs with 4 bonded components, we have a tetrahedral. If we have 4 pairs, but 1 is a lone pair and 3 are bonded, then that's going to be a trigonal pyramidal. Now, what happens if I take away another item, another atom, and put on another lone pair? Well, now I have 2 bonded, 2 lone pair. You can see the basic shape is still a tetrahedral, but I can't see the lone pairs. What I can see is the oxygen and the 2 hydrogens, and we call the shape bent. Okay, so we have 4 pairs, 4 connected pairs, 2 bonded, 2 lone pairs. That gives me bent. Now, will I always have 4 pairs out? Not always. Sometimes those 2 pairs will connect so that we have 3 atoms with no lone pairs, right? And here you can see the examples with a double bond. Now, when we make a double bond like this, what happens is the 2 that were sticking out kind of pinch together, and the 2 that were sticking the other direction are now even out there even further. When that happens and those 2 pinch together, we get a new bond angle of about 120 degrees. And so this whole molecule is actually planar. And notice all the lines are in the same plane. So the furthest I can get away is 120 degrees. In this situation, we call it trigonal planar. So we have trigonal pyramidal when we have 3 things connected, and we have trigonal planar when 3 things are connected. The difference between the two, remember, is that lone pair. Trigonal pyramidal had a lone pair of electrons. Trigonal planar doesn't have any lone pairs. We've also seen a case where we've had 2 atoms with no lone pairs in the terms of a double bond, right? We had 2 double bonds. There's my CO2. We also had HCN, which had a triple bond, and it would fit the same idea here, where you have 2 atoms with no lone pairs. The furthest they can get away then is 180 degrees, and we call that shape linear. Now, those are the only 5 shapes I need you to know. Okay, so we had tetrahedral, we had trigonal pyramidal, then there was bent. Those had 4 electron pairs around the central atom. When we have 3 central pairs around that atom and no lone pairs, then we get trigonal planar. That's our 4th shape. And then when we have no lone pairs and only 2 atoms connected, we get linear. Now, what I want to do next is take electronegativity and shape and blend them together so that we can talk about polar molecules. So polar molecules would be molecules with ends, molecules that have a polar moment. Now, for that to happen, a couple things have to be true. Molecules that have a positive and negative end require 2 things to happen. 1, you have to have a polar bond. So the first thing we'll do is figure out whether or not we have a polar bond. If we do, right, then, and of course that's from the electronegativities, then we're going to look at what's called symmetry. Symmetry can cancel out the effects of that polar bond, right? So we'll have to determine the molecular geometry and then see if the electronegativities are going to cancel out from that. Now you're going to be hitting a lot of these topics with a very simple question, and it's going to be, is it polar? So I'll give you a molecule like HF, and I'll ask, is it polar? Well, here we have 2 points in space, so we don't have to worry about geometry at all. All we have to do is look up the electronegativity values. Hydrogen we said was 2.1, fluorine is 4.0. I subtract those 2 and I get 1.9. That does fall in the category as polar, so yes. How about water? Now water, you might already know is polar, right? So if you've taken an A&P course or a biology course, maybe even another chemistry course, the one thing you might remember is that water is polar. It's the universal polar solvent. All right, let's figure it out though. Okay, so hydrogen is 2.1. I go back to my electronegativity chart, and I can find oxygen is 3.5 according to the table. So 3.5 minus the 2.1 gives us 1.4, and so yes, this is a polar bond. But what about the shape? Well, if we flip back a few slides, we'll see that the shape for water is bent. Okay, so if it's bent, I can draw that shape out, put oxygen in the center, and since it's bent, it's going to look like that. Now we know the oxygen value is higher than the hydrogen value, so it means the two arrows would point at the oxygen. And so now, are those two arrows going to cancel out? Well, we might say yes, because left to right, they would cancel out. But if we look at the direction of up and down, we can see that up, both of them are adding together to push up. Since we're pushing together and not against one another, it's not going to cancel out, which means our polar calculation holds true for the molecule. Yes, it's polar. How about ammonia, NH3? Well, if I look up ammonia, NH3, nitrogen is 3.0, hydrogen is 2.1, we have a difference of 0.9. And once again, if I draw that out, right, that was our trigonal pyramidal. So our trigonal pyramidal is going to put nitrogen at the top. We can have a hydrogen coming out at us, another hydrogen coming out at us, a hydrogen going back away from us, and the lone pair on top. All the hydrogens here would be pointing towards the nitrogen. And of course, left to right, they would all be balancing out, but up and down means they're going to be pushing it up. So that means that yes, right, we have a polar molecule. How about CCl4? So carbon is 2.5, chlorine is 3.0, 0.5 difference. So we would say no, or it's right on the line, so maybe. But if I look at a tetrahedral and I draw those arrows, they're all working against each other. And so the symmetry is going to cancel it out anyway, and we don't have to worry about it. All right, how about CO2? Oxygen is 3.5, carbon is 2.5, the difference is 1.0, definitely a polar bond. But remember, when we draw it out, we get carbon in the middle, double bond oxygen, double bond oxygen. The arrows would point to the oxygen, and it's like it's playing tug of war against itself, right? So it's going to cancel out any polar effects. And so that means no, it's not polar. All right, so there's a few examples. If you look in your lab components here, we'll have some more examples for you in the worksheets. And that way you can figure out polarities and see if they cancel out each other. All right, the last topic we have for the show, and so I'm going to push a little longer in the segment. Typically, as you know, I've been trying to stop between 15 and 20 minutes. We're about 18 minutes in, but these are the last topics we have. So we're going to go ahead and knock these out, and that way we can just call this the final segment. So intermolecular forces, what holds the molecules to each other? Okay, so there's intramolecular forces, and then there's intermolecular forces. Intra are forces that happen within the same molecule. For those of you going into the medical profession, you'll see this with, like, DNA, the alpha helix. That's an intramolecular force where the proteins are bending certain ways and holding on to each other. But when it's smaller molecules, we don't really see intra, we see a lot of inter, which means molecule A is now interacting with molecule B. Okay? Now we need those interactions to change phases because it's the attraction between the particles that are going to force it to become either a liquid or a solid. So if we didn't have interactions between particles, all of these particles would rather be a gas. All right? Now the weakest of these intermolecular forces is called the van der Waals forces. Okay? And there are a couple kinds. We have the dispersion forces, and then we have dipole interactions. Now, dipole interactions are going to depend on the number of electrons that are involved. Dispersion forces are like basic static forces, things that are moving near each other. The bigger they are, the more static electricity they generate, the more attraction they'll have. So you can think about it when you're combing your hair, right? I don't have that anymore, but if you comb your hair, you can get electric static coming on the comb, right? That's the same sort of idea. When you pass two things past each other, they form a static, right? Now for dipole interactions, the more electrons we have, that stronger the force will be. So the bigger the molecule is, the more dipole interactions we can have. Now, dipole interactions depend on the number of electrons and how strong those forces are going to be. All right, so fluorine, for instance, is a gas. It's only got 7 electrons in its outer shell. It's a small molecule, 14 electrons per molecule. Not a whole lot of stuff going on there. I slide down in the same group just a couple of atoms, pump up the number of electrons, and I've got a liquid. Go a little bit further, get some more electrons, and I get a solid. Okay. Now, dipole interactions occur when polar molecules are attracted to each other. So dispersion, again, is just things that are passing by each other. The bigger they are, the more electrons they have, the more static they'll generate. For dipole interactions, they're going to occur when polar molecules are attracted to each other. So these are stronger than your general dispersion forces. Opposites attract, but not completely hooked like in an ionic solid. So when polar molecules are attracted, what we're going to see is the HF here. We have a partial positive and a partial negative. What ends up happening is between the two molecules, we'll get an interaction between the partially negative and the partially positive ends. If I draw this out to a larger scale, you can see we start to increase those interactions, and that can generate a liquid or possibly even a solid, right? And so that's it for dipole interactions. If you've got any questions about these chapters, make sure you get a hold of Mr. Caro or seek out some tutoring. Either one would be fine. You can set up an appointment with Mr. Caro, with myself, to do tutoring, or come in for a student hour visit if you'd like. I'll be setting those up, and so you'll know what times you can come reach me without having to make an appointment. If those times don't work for you, don't hesitate. Make an appointment with me. Get help as soon as you need it. I'm a personable guy. I'll do everything I can to help you get through this and be successful. All right. Talk to you soon.